Hello, everyone. Today we will be talking about plasma diagnostics. So basically, how you measure parts of the plasma. Okay, so why do we care about diagnostics? As a preface, I will say I'm going to ask lots of questions. Obviously, this is a video, so when I ask a question like this, if you would like, pause the video for a second, try to answer it as best you can, and then continue, and you'll see the answer. These are not questions that you're supposed to have the answers to, but it's a good exercise to try to search around and come up with answers if you can. It'll help the learning stick. Okay, so what could we diagnose in a car? So like what are some things that we might want to know about the operation of our car to help us drive safer, understand what the car is doing, understand how fast we are, that's a hint. So think about that for a second. Okay, so the big one is speed. We want to know how fast our car is going. That comes from how fast the wheels are spinning, gas level, how much fuel do we have left, engine RPM, oil temperature, fuel mileage. All these things are useful metrics to know, and we diagnose them in different ways. But that's what we're doing. What about a computer? Okay, so similar actually. Temperatures, we can like memory or storage use, how much of our processor is being used, how much power it's taking, what our battery level is at, all that kind of thing, all those kinds of things. So these are just examples to get you thinking about what we might want to diagnose. So what would we want to measure in a plasma? Actually similar. So temperatures, which is, as you remember, is a metric or is a measure of average energy of our plasma. Densities, how much stuff do we have in a certain volume? Composition, so that's like what kinds of gases. In the picture on the right, the plasma ball, there's probably like 5 or 6 different species of gases, argon and xenon and stuff like that. Magnetic fields are really important because we apply magnetic fields to plasmas. Plasmas also make their own, so we want to see the magnetic fields that they produce. We can learn things about the plasma that way. Electric fields produced by the plasma, flow velocities. The plasma in a lot of cases is actually flowing, kind of like a fluid. So we want to know those velocities and how they interact. Power going in, coming out, that's a big one. Obviously, we put the power in usually, but a lot of times it leaks out. We want to kind of find how it's leaking out. And then fusion, like how much fusion are we doing is obviously a big thing that we want to diagnose in a fusion plasma. Okay, so why is diagnosing plasmas hard? Take a second and think about that. Okay, so the big one is they're hot. They have a lot of energy. They're also electrically charged. These are all things that can damage the stuff we put in to touch them. So if we have this really hot, we have magma, it's hard to stick a thermometer in because it's going to melt. And that's similar to plasma. They can be super energetic. So actually sticking things into them, probes or other diagnostics can be damaging to the diagnostics. They're hard to get to. So most of the plasmas we produce on Earth are under vacuum. So they're in big metal tanks. We pump out all the gas, we put in a little gas back in, and then we add a bunch of energy and we get a plasma. And that makes it kind of difficult. You have to put stuff in the vacuum. Those diagnostics have to be like, able to survive under vacuum, so that kind of thing. And then also a lot of the plasmas we don't study as much in fusion, but in the field are space plasmas. And obviously those are hard to get to. You have to launch something on a big rocket, fly it to whatever plasma you're interested in. So that could be around the sun or in certain areas around the Earth. And that's difficult and expensive. So these are all things that make diagnosing plasmas hard. And then they're electrically charged. So when you put a piece of metal in a plasma, it interacts electrically because there are all these free electrons flying around. The other big one is that they are susceptible to interaction. So that means by measuring them, there's a chance that you can change them. So that's a big deal because if we have a big bucket of water and you put a thermometer in, that's not really changing the temperature of the big bucket of water. It has kind of thermal inertia is what we call that. My little thermometer is not changing the system. But if we have an electrically charged hot plasma and I stick a thermometer in, it might pull current out of that plasma, like basically pull electrons out, or it might do something else that actually changes the plasma I'm measuring. So I'm not measuring what I think I'm measuring. So these are all things we have to take into account when we're diagnosing plasmas. Okay, so just roughly, this is kind of an overview of the talk today. We're going to look at a bunch of different ways to measure a plasma, and they vary pretty drastically. So we can look at the light that plasmas emit. So if you've seen like a plasma ball, it's emitting light, right? You're adding energy to a gas and you get light out and some other things. So we can do this. That's called spectroscopy, looking at light. So we can do it passively. So the plasma makes light. We just kind of collect it. We stand back and we look at the light and we can diagnose things about the plasma. Or active. This is like we're actually exciting something about the plasma, something specific. We're exciting it in a specific way. We're adding energy and it produces light in kind of a predictable way and we see what happens with that. So that's active spectroscopy. We can touch the plasma, which is probes, actually putting things into the plasma. We can measure magnetic fields that the plasmas produce. This is super important. This is with magnetic sensors. This is another kind of hands-off passive way of measuring plasma. You're not changing the system, you're just measuring kind of what it's doing. There's this kind of specific one that's called interferometry, whereas we pass light through the plasma and see how it slows down or reflects. We'll talk about that. And then the other big one is we can collect neutrons. So when fusion happens, the way we're trying to do fusion with deuterium and tritium, it produces a neutron. And neutrons are not electrically charged, so they just fly out of the plasma. And that's a very useful way to measure, especially fusion, but other things about the plasma as well. So we're going to talk about all these in more detail. Okay, this is just a side note of in the lab or in the facility, what we're actually measuring almost always comes down to voltage and current. These are the actual two things that we get out of almost every single diagnostic. You then translate that by calibration to some real value, some density or temperature or magnetic field. But most of the time, this is just kind of a good thing to remember is that most of the time it comes down to measuring voltage current. We do it something like this, which is a multimeter on the right. But that is just something to kind of remember that in the lab, usually what you're doing is you're taking some physics thing, a magnetic field, and you have a combination of circuits and wires and such that translate that to a voltage, and that's what you're actually measuring. All right. So spectroscopy, we're going to do active and passive. All right. So first, some basics. There's going to be a decent amount of background in this. But so spectroscopy is measuring light. How can a plasma produce light? There's a few different ways. We're going to talk about all these in more detail. So charged particle acceleration. So if you remember, accelerating is changing direction or changing your speed. So if I'm going really fast, if I'm an electron and I change direction really quickly, that's going to emit light. That's called synchrotron radiation. If I'm an electron and I slow down all of a sudden, I see a nucleus and I really slow down quickly, that's also changing my acceleration. So that's called Bremsstrahlung, which is a German word for braking, as in like braking your, the brake in your car. There's also thermal radiation. So this is just charged particles moving around kind of in a big glob, and that produces radiation we call thermal radiation. So these are all ways that charged particles can produce a light. And obviously we have plasma is just a bunch of charged particles. So there's also a thing called line emission. So this is when you have electrons that are bound to a nucleus. So it's not totally ionized. It can be partially ionized, meaning if you have a Z equals 6 atom, it has 6 protons, 6 electrons. If you remove one of those, you still have an ion and an electron, but you still have 5 other electrons floating around your nucleus. These are called bound electrons, and they can jump up and down energy levels. So you can see this picture on the right is a rough diagram of this. This is kind of a classic image of an atom. And if you add some energy, they can jump in energy level. They actually go farther away. That means they have higher energy. And then at some point they might relax and they go back to a lower energy state. And the difference in energy between the higher and lower energy state is emitted as light. So this is called line emission, and I'll explain why in a little bit. Okay, so as a reminder, light is electromagnetic radiation. So we use the words interchangeably, but EM radiation is this huge range, which we characterize as the wavelength. So it goes all the way from, what's that say, 10 to the minus 5 nanometers all the way up to 10 to the 3 nanometers. So that's 8 orders of magnitude. That is all electromagnetic radiation. The light we see, the light our eyes is sensitive to, is just this little range, which you can see there. These are all the colors that we can see, but they're just on the spectrum of light. Remember that these are oscillating electromagnetic fields. It's not super important for this talk, but just as a reminder that it's all the same thing. When I say light, I mean electromagnetic radiation and the other way around. These are X-rays and gamma rays and radio waves, all that stuff. Okay, spectrometers. This is the actual equipment we use to measure light. And the kind of core premise of this is that when you have a beam of light, say sunlight, which is a whole bunch of colors, right? It looks kind of yellow to us, but it actually includes some green, some purple, some red. It includes all of that. But it shows up to our eyes as white. And it also shows up to our devices as kind of a single thing. So what we want to do is we want to separate those out, and we use something to refract it, or a diffraction grating. So one version of that is a prism. So the classic, like if you look at a piece of crystal hanging in the sun, you can see it produces a rainbow. What that's doing is basically just splitting up the light into its component colors. We can also do this with something called a diffraction grating. These do the same thing. And what they do is they basically change how the light is reflected depending on the wavelength of the light. So for a blue light, it might get deflected a little less, and for a red light, it might get deflected a little more, and that spaces out your spectrum, and you can see exactly what colors are, or what frequencies. This is all the, frequency, color, it's all the same thing. What colors are there. Okay, so a photodetector is another way to measure light. This isn't measuring a specific frequency. This is just measuring kind of a quantity. And don't worry too much about the details, but basically what this is doing is you get a little photon. The photon hits a specific material and it knocks off some electrons. You can see that's kind of in the middle here, this photocathode. Knocks off an electron, and then those electrons are multiplied down this kind of cascade. These are all just materials that when an electron hits them, they spout off 2 electrons. So you go from a 1 photon or a very small signal or very small energy wave, and you can create a bunch of electrons, and then you can measure them. Remember, we measure current and voltage. So then you get some voltage measurement, and you can calibrate that back to say, okay, that was this amount of photons or this amount of energy of light. This is how cameras work. So CCD, CMOS, these are like the camera sensors in our cameras and phones. They can be a big range, but this is kind of a classic thing. And then another one is, sorry, the other way around. That was a photomultiplier tube. The way our cameras work is the picture on the right, which is a semiconductor, so a piece of silicon, and it basically measures some voltage when radiation hits it. So that's a solid state measure. But these are all just ways of measuring light. Okay, another interlude, an interlude to our interlude. We'll talk about Doppler shift. So Doppler shift is the change in frequency of wavelength due to relative motion. So this is the classic. If a fire truck's coming at me, it's producing a siren. Say that siren is at a single pitch, so a single frequency the whole time. As it comes closer to me, what it's doing is as the object is moving, so in this case, the ambulance, the waves are actually being bunched up. So I hear a higher frequency pitch than is actually being emitted. And then once it goes past me, it's now going away. So the peaks or the waves are kind of spread out. So I actually hear a lower frequency than the one is actually emitted. So the same frequency is emitted the whole time, but I hear this kind of high pitch and then it goes down. We all have had that experience. So this happens in light too. If the object is moving towards you, it will make the wavelength shorter, so make it bluer. It's called blue shift in kind of astrophysics. And the other way, if the object is moving away from you, it creates redshift. So we use this in a pretty specific way in plasmas, and it's called Doppler broadening. So if I have this signal, so this is my energy. Energy is also equivalent to wavelength in light because we know how fast it's going. So if this is my energy, I have some error here, which is due to a few things, including kind of quantum mechanics. But say this is a relatively unbroadened, so it's a single energy. These photons are coming at me all with a single energy. But what if they're kind of moving around? What if the electrons that are producing them are just kind of jiggling around? That will make some of them higher energy. I will perceive them as being higher energy, this blue shift, and some of them will be red or lower energy. And what it does is it takes this kind of single monoenergetic peak and smears it out, and it's called Doppler broadening. And what that does is it tells us the temperature, right? Because the temperature is the average jiggle motion. So it's an important thing that I'll mention a few times, but this is a way we can actually, just from a single frequency of light, we can tell the relative temperature of the average energy of something, basically how fast they're jiggling around. All right, so I talked about this briefly, but I'll mention again. So types of spectroscopy are passive, which is, in this case, it's from a satellite on the Earth. The sunlight is hitting the Earth and it's being reflected, and we're just measuring that. We're not interacting with the Earth. It's just kind of the system as it is, and we are looking at the light that it produces. And then active is we're actually doing something. So in this case, our satellite would be beaming some radio waves, say, down at the Earth, and then seeing the reflection coming back. So we're interacting with the system. It can be very minor interactions, but we are doing something to the plasma to get a signal out, and then we measure that signal. So these are the two different ways. So we're going to separate the two in that way. Okay, so I mentioned line radiation before. This electrons jumping around energy levels. And because of quantum mechanics, and you can go into this, basically what that means is that the electrons can't be anywhere relative to the nucleus. They have to be in these discrete or quantized energy levels. And so when they jump around, they emit light. So in this case, my electron, so the yellow is an electron, is at n equals 3. So that's just an energy level, the third energy level. And it goes down to n equals 2. The difference between these two energy levels is a number, is a specific number. And it will release that amount of light. And then if you translate that energy to light, you get this red line, 656 nanometers for this specific atom. So what that tells me is when I measure 656 nanometers, I know exactly that this electron made this transition in this atom. And when you add them all up, so this atom has these energies. The energies are dependent on the kind of what type of atom, so carbon or oxygen or hydrogen. And it makes kind of a fingerprint. We'll see what that says. So it makes this like spectrum, so this like series of lines. And what that can tell us, it can tell us kind of what type of gas this is, because each gas has a fingerprint, and that fingerprint is this specific combination of these lines. So that's what I mean when we talk about line radiation. So this is just reviewing what I said. When heated, electrons go to a higher energy level, and then at some point they relax, they go back down to a lower energy level, and they release that difference in light. You can use this equation, which is a pretty classic one, to calculate. So N1 is our initial energy level. So in that case, this would be equal to 3. And then N equals 2, or N2 is the final, the destination. So that would be N equals 2. So this would be 3, this would be 2. This is a constant R, and then Z is the charge of your nucleus. So it's basically what element you have. And then 1 over lambda, lambda is our wavelength. So that tells us kind of the energy of light that's released in this reaction. And again, because we know C, so frequency is F, lambda is wavelength. So we multiply those together, we get C. We know C. So if we know lambda, we know frequency. And then our energy is proportional to those two. So we can write that as this is a constant. C is a constant speed of light. H is a constant. That's Planck's constant. And then if we know this, we know the wavelength, we get the energy. All right. So briefly, what is a line? Again, a line is just like a very specific frequency. So a single energy or whatnot. But because quantum mechanics, there's a little fuzz, we can't know exactly the energy. What we get is we get a peak, and that is here. So you can see that this is actually real data that I collected in college. And these two lines are from an element. And if you basically add up all the intensity of light going horizontally, you get the plot on the right, which is these two peaks. And no matter how cold you get your gas, so they're not jiggling, there's none of this Doppler shift, you'll still get some kind of peak that's not just a perfect line. And if you heat them up, that peak will like mush outwards, spread out by Doppler shift, which is what we talked about before. Okay, and then this is the fingerprint I was talking about. So each element has a unique spectrum, so a set of lines that it produces depending on the energies of its energy levels. And if you look at if you heat up a gas, it will produce all of these lines pretty predictably. So there's a pretty easy demo you can do with this. Yeah, so we can tell the kind of composition. So that's what we use in plasmas a lot of times. We look at the spectrum, we can tell, okay, this is hydrogen and oxygen because I see all the oxygen lines are strong, and then I see all the hydrogen lines are strong. That's an example. You can also do this absorption, so the other way around. So if you shine light through a gas, it will only absorb certain frequencies. And it's the same. So this is absorption. So if there were light shining through a cloud of oxygen at me, I would see all the colors but the ones it absorbs. So that's another way we can do this. Again, this is more data I took in college, but this is just a broad spectrum. So you see, remember this lambda's frequency or wavelength, and you can see all these different things. We've kind of labeled them. So this is krypton 2. So that's krypton. You've removed 2 electrons. And then these are the kind of wavelengths it produces. So you can see that one's there. Krypton's down here. We were changing the flow rate. So you can tell a lot from these spectra. And this is all passive spectroscopy. This is what I mentioned with absorption spectra. So if sunlight is a continuous spectrum, so it has all the colors, and if we apply it to some gas, it will excite the gas, and that gas will emit its line spectrum. So here, so if we're looking off to the side, right, the sunlight's going horizontally. We don't see the sunlight, but we see it excite some gas, and then it emits perpendicularly. That's what we see. And we're on the other side of the gas, we would see the kind of the missing lines, and that's called absorption spectra. This is used pretty widely in astrophysics because if you have a planet and there's a sun behind the planet might have an atmosphere, and that sunlight goes through the atmosphere. That atmosphere, whatever gases are in it, absorb their spectra, so absorb these lines, and then we see the resulting thing. So we can see that that's how these like exoplanets that are light years and light years away, that's how we can tell the composition of their atmospheres because we're looking at what frequency of light are absorbed by the gases. All right, so when do we use line emission in a tokamak? So we use it in the scrape-off layer. So if you remember all these things, like this is an example of the kind of magnetic bottle that we build. So that's the red part. So that's confined plasma. But outside the confined plasma, basically between that last closed flux surface, which is the kind of last confined plasma part, and the wall, there's still plasma there. It's much lower temperature, and we call it the scrape-off layer. And that is a low enough temperature that it actually has line emission. So when you see a picture like this, the densest, hottest part of the plasma is in the middle, excuse me. And we just can't see it because it's not emitting light at the frequency that our eyes are built for. So what we see is we see the colder plasma around the edge. So it's kind of a good thing to remember when you're looking at this, that you're actually not seeing the hottest, densest stuff. And again, this happens because the plasma, these line emission only happens when there are electrons bound to ions. So when you have some kind of bound system. And in the middle of a tokamak plasma, there's nothing bound. Those ions are completely stripped of their electrons. Everything's freely flying around, so you don't get line emission. Space plasma. So spectroscopy is really important because we can't interact with space plasmas. In a tokamak, we can do things which we will talk about. We can do active spectroscopy or other kind of diagnostics that require interacting. But with a space plasma that's light years away, obviously we can't get there. So we just look at the light, and that's most of astronomy and cosmology is looking at the light that space plasmas emit. Oh, okay. So this is what I mentioned before. So if we have our planet here, far, far away, and we have its sun, its star behind it, so its sun. The light's going to shine through the atmosphere, this kind of thin film. And then what we'll see is we'll see the whole spectrum coming from the star, which we know is this kind of broad range, and we'll just see the missing colors. And that will tell us the composition of the atmosphere of this exoplanet, which is very cool. You can also do this for, like I mentioned, kind of everything in space, but planetary nebula or supernova, all these things, we can tell their composition by looking at the emission spectra. So what colors they are emitting, what colors we see. And you can see this is kind of this big slope is just some background. But you can see the spikes are magnesium, see neon here, silicon. So we can tell the actual composition of these faraway objects by their line emission spectra. All right, so the next thing, the next way that plasmas produce light is called bremsstrahlung, which I mentioned. So any acceleration of a charged particle produces light. That's just electromagnetism will tell you that. So there's two different ways you can change your acceleration. You can change your speed or direction, and this is changing speed. So it's slowing down, which is most often, or speeding up. So in this case, you actually do see a curve, but the curve is not what we're interested in today. This is an electron, this is an ion, or this is a, yeah, say an electron and an ion. And what it's doing is it's kind of swinging by, but the ion's actually pulling it. So we're changing our speed. We're either, it's called a collision in this case. So even though they're not physically colliding, their forces are interacting and they might be attracted to each other. Or if it's two ions, an ion and an ion, it might be slowed down by one or the other. And that will cause a change in speed and will produce light. So bremsstrahlung is German for to break and radiation. So we're breaking radiation. We're slowing down, or in some cases speeding up, and that's causing radiation. And these happen because of collisions. And what we mean by collisions are when two charged particles interact via their charge, so their electromagnetic field. Again, this is a example. Don't worry too much about the curve because what we're interested in is the change in speed because this is an electron being kind of like swooped and accelerated by an ion. Bremsstrahlung is usually emitted in the X-ray spectrum. That's why we can't see. So it's most of the light coming from the center of the plasma. That picture I showed a bit ago is bremsstrahlung, and that we can't see that. It's X-rays. So that's why it doesn't show up in cameras. We can learn something from the shape of this continuous spectra. So these aren't, unlike line radiation, where the emission is very specific. It only comes out in certain colors. This can be emitted at a lot of different energies. So we get this kind of broad range of spectra. And we can tell, so each one of these lines would be one measurement of a plasma. And there's some minimum wavelength. But then we can see this, like the shape changes. And what we're doing here is we're actually increasing the voltage. So this is basically changing the energy of the interactions. Anyway, so we can learn a lot about the plasma by looking at the bremsstrahlung radiation. And one of those things, so you can compare basically this to a known equation. So this would be that equation. And it can tell you something about the energy and the density of the plasma. So the other way we can change acceleration is by changing direction. So when we are being curved, so even if our speed isn't changing, if our direction changes, that is an acceleration. If these are charged particles that are changing direction, they emit light. When they're going around kind of a circle like that, we call it synchrotron radiation or cyclotron radiation. They're almost synonymous. It just kind of depends on what frequency they're being emitted at. So if you can see this picture, this is a synchrotron, which you might have heard of it. They make specific devices that produce light in this way. But tokamaks, you can also, you can kind of picture this as a skinny tokamak. There are particles going very fast toroidally, so around the donut. And so they produce synchrotron radiation. It's not as much as bremsstrahlung, but it is not insignificant. So it's something we definitely think about. I'll mention, yeah, so synchrotron is usually higher energy, so X-rays, and then cyclotron is usually slower. They're not going quite as quick, so it's lower energy, and it's in the microwave region, which is down here. So what would happen? When would this happen in a tokamak? I guess I just mentioned that as the particles go around toroidally in the B field, they produce synchrotron radiation. So this is kind of just a neat anecdote. The brightest synchrotron source in the world, again, a lot of synchrotrons are basically devices like this one in Brookhaven. So you can see the scale. These are cars down here. This is a huge building at Brookhaven National Lab on Long Island. And they run these charged particles super fast around in a circle to produce a light. And I'll also mention in the picture before, the light goes off kind of tangentially. So if I'm turning left, you can see I'm turning left, it kind of goes straight as if I wasn't turning. So in our synchrotron, the light, maybe say it's going around counterclockwise. At all these kind of stations, there's a beam of light coming out tangentially, and you can use that for all sorts of different things. It's just a kind of a useful source of super high energy X-rays. In this case, the Brookhaven National Lab, it's 100 billion times brighter than the sun, which I just thought was very interesting. So the kind of last type of radiation is thermal radiation. This is this jiggling of atoms we talked about very specifically when electrons or protons, but electrons are slowed down, they produce bremsstrahlung. When they change direction, they produce synchrotron. What if they're just kind of jiggling around? So it's the same two concepts, but you just kind of average it over a hot gas or a hot plasma, and you get thermal radiation. So we experience this quite often in any kind of heating, and you can you can feel the heat without interacting with the fire, say, and this is a very similar process. So there's this kind of jiggling around of charged particles, and that produces a spectrum of light. We call this bolometry. That's the practice of measuring radiated power, this kind of thermal radiated power. And don't worry too much about this, but basically what it is, it's this piece of metal. It's not anything super special. And then this very particular, basically connection, a wire. And you can measure the voltage across them, or you can measure like the length. Sometimes they'll have ones that the actual length of this coil, say, kind of stretches and it contracts depending on the temperature. And that can tell you the temperature of this material, and that can tell you the power that's going in. It's basically how much is being heated up. And that gives you a sense of the radiated power. So that's kind of the total thermal radiated power. It's usually in infrared, in visible regime. So things that are hot, you might see like a hot piece of metal is emitting at kind of very red side of visible spectrum, and it might be emitting light. And so if you have a hot piece of metal, it might be emitting light, and that's hot, and you can kind of feel that, but it might cool down like a hot pan. It doesn't glow, but it's still emitting light. So that's in the infrared, so just below the red spectrum. Okay, another thing we can do with light in a tokamak is using fast cameras. So these are high-speed cameras that get used for all sorts of purposes in the world. And one of them is fusion. So we can basically look at a tokamak plasma. Remember, I'll play this video in a second. Remember that the actual hottest, densest part is in the middle on each side. And basically, but it's not producing light that the camera can see. So we just are kind of looking at this light. And but we can still learn a lot about the tokamak in these plasmas. You can see in this video, which I'll play. I'll mention that this is from MAST, which is the mega amp spherical tokamak in the UK. So this is a very slowed down version. So these shots at MAST are about a second, and they've stretched it out to 30 seconds or so. But even then, things are still happening very quickly. And you can see it's kind of growing. Now it's kind of left. It's not touching the wall as much. It is still touching the wall there. Not sure what's going on there. You might learn something. Maybe it's rubbing against the wall. Maybe that's a gas port. You can see it's kind of flickering. Those might tell you something about some kind of instability. You can see it's glowing a lot hotter, and it's getting quite smaller. So I think we're headed towards a disruption. And then, nope, it actually didn't disrupt it. It went out quite nicely. So you can learn a lot by just looking at the visible light that's emitted. Another thing we can do, this is independent of, not independent, this is just another example. So this is HPTP. This is the tokamak we have here at Columbia. And this is a 100,000 frame per second video of a shot. So these shots are about 10 milliseconds, so much quicker. And you can actually see some filament structure. You can see it rotating. So you can learn a lot from this kind of imagery. The other thing we can do in fusion is we use them not for plasmas, but this is a pellet. So this is the way we fuel the plasmas. We take these frozen kind of wine cork sized hunks of gas, and we shoot them into the plasma. This is an experiment that's done at Columbia, and this is going very fast. And so we can use these fast cameras to measure. So there are other areas in fusion research that use fast cameras. Okay, so next we're going to talk about active spectroscopy. So this is when we're interacting with the plasma and looking at the light that comes out, kind of in a slightly more predictable way. It has its pros and cons. We can learn things that we can't learn from passive spectroscopy. So the first one is charge exchange recombination spectroscopy. It's a big word. We'll break it down. So first of all, what we're doing, this requires firing particles into the plasma. We do this, it's called a neutral beam injection, which we've talked about in this series of videos so far. And it's a way of heating the plasma. We get a gas going super, super fast, and we fire it in the plasma. Usually it's the same gas that the plasma is made of, and those particles run into the plasma and knock them around, and they add energy to the plasma. It's one way of heating a tokamak plasma. And we can actually learn something by looking at the light that this produces. Okay, so NBIs are neutral beam injection. So that gets shot in, it's kind of injected around here. And then we have this line of sight. So then we're looking at the light that's produced in this area. And what we're going to write out a little equation that's going to go step by step. So H naught, this is our hydrogen. It's not charged as neutral. That's why neutral beam. So there's not charge. So it's one proton, one electron. And we're injecting into the plasma, and this is kind of our plasma gas. So plus Z is the ions in our plasma so they're totally stripped of their electrons. So it's just like, say, like 2 protons or whatever. or one proton in the case of hydrogen plasma. Okay, so then we get this neutral particle from our NBI interacts with whatever gas is, whatever ion is in the plasma, and it gives it an electron. It gives it its electron. It collides, and one electron gets pulled from the neutral beam particle on into the plasma ion. So then we have our proton, which is now, or the thing we injected, but it lost its electron. So now it's just a proton on its own. That's what the plus is. So it'd be +1 is another way to write this. And then we get our the species in our plasma, but it's Z-1. So now it actually has one electron. And that electron is kind of by necessity in an excited state. We talked about this line radiation thing before. Same thing. That's in kind of a higher energy level because it just got stripped from another, from a neutral particle. That the star means the excited state. So then what happens is that electron then relaxes into a lower energy state and releases light. So gamma is kind of the universal term for light. So this is a way, recombination is meaning you go from an ion to a bound state. So you basically attract an electron. So that's what's happening here to the atom in our plasma. It goes from free, just a proton on its own or just an ion on its own. Then it gets an electron in an excited state and then an electron relaxes. And we look at this light. So the light of the relaxing plasma ion is what we're looking at in this case. We can tell a bunch of things. So we talked about line radiation tells us the species. So this can tell us about the actual species concentrations we have in the core of a plasma, which is really interesting. It was hard to get otherwise. And we can also tell something about the energy because we've put that electron onto that plasma ion, and then it's still jiggling around at its temperature. So when it emits that light, we get that Doppler broadening, which we talked about before. And so that can tell us something about the temperature in the middle of the plasma. Another way we can tell temperature and density in the middle of a plasma, and instead of injecting particles, we inject light. So in this case, or in Thomson scattering, is a laser. So we send light in the plasma with a pretty high power laser. In this case, the light is actually interacting with free electrons. So the last case, we are injecting these neutral particles and they're interacting with the ions in the plasma. In this case, we're injecting light and they're colliding with or scattering off of the electrons in the plasma. So we measure the Doppler shift. So this is the same thing. So the light comes in here to get to our spectrometer, our collective optics. Over here, it has to scatter, has to bounce off and change direction. We're not going to see any of the light directly from this laser because it's pointed in a different direction. And this is a really common and really powerful diagnostic to tell us about the electron density and the electron temperature, which if you multiply together, you get pressure. So this is a super important diagnostic, Thomson scattering in tokamaks. You can also get tokamak scattering in space plasmas. So we think usually about spectroscopy and diagnostics in space plasmas as being passive. So we're just looking at the light. And this is similar. We are interacting with it. But in this case, this is a picture of a solar eclipse. And you can see the light from behind. Basically, the moon is blocking out the sun right now. So it's a total lunar eclipse. And the light from kind of behind this solar prominence, this red thing is a solar prominence, one of those big arches out of the sun. And the light from behind it's interacting with it and scattering off of those electrons and then coming towards us. So this is actually kind of a way that nature gives us Thomson scattering. Okay, so final one of this active spectroscopy is laser-induced fluorescence. This is very similar to Thomson, except this is interacting with the electrons that are still bound to an atom. So in this case, it's the same setup. We fire a laser into our plasma. This is the laser photon. It excites an electron that's bound to an atom. So this could be a plasma because these could be partially ionized atoms. And then that electron relaxes and emits light. And so it's a very similar process, but instead of kind of colliding with and interacting with free electrons, this is interacting with bound electrons. So why can we only do this for low temperature plasmas? Because low temperature plasmas still have electrons bound to atoms, to ions. In a high temperature plasma, everything is dissociated. So all the electrons are flying around free and all the ions are flying around free. So there's no bound electrons for this to interact with. So we don't actually use this in tokamak plasmas. This gets used in lower temperature plasmas. Okay, next we're going to talk about probes. This is actually poking the plasma, so interacting with it directly. Okay, so this is the image we're going to use. This is a plasma, if you can believe it. Each of these blue dots are electrons and the red circles are ions, and they're just kind of floating around. And then what happens if we put a piece of metal? So in this case, our gray circle here is just a piece of metal. What happens if I were to put a piece of metal in plasma, if you have any guesses? This is not an easy one. None of them are easy, but this one is a little tricky. So what happens is actually because the electrons at one temperature, so if everything is at thermal equilibrium, so the ions are the same temperature of the electrons are much lighter, meaning they have less mass, so they're actually moving around quicker. And that means they're actually going to collide with and kind of stick to our piece of metal faster than the ions are. So the metal is going to become negatively charged. We call this the floating potential. So if I just measure the potential, so V is our symbol for electric potential. So if I measure the potential of this, I'm going to measure a negative value. But what if I then grounded this? So basically, I gave this little ball of metal a path to ground. So that's kind of what, in this case, this is showing. So if I connected it, if I stuck a big rod of metal into the earth and gave it kind of an infinite sink, is what we think of as ground. So a place for the electrons to go, a place for the ions to go, what would happen? Basically, that's exactly what they do. They go to ground. And so these are our little electrons. They're now in our metal. This is all our grayish metal, and they kind of scoot on down, and we can measure the current of these electrons passing because it'll happen continuously, and we can also measure the voltage. So then what we can do, so that last time we weren't actually applying any voltage, we're just measuring things. But this time we can actually apply a voltage. So we can take our piece of metal and charge it to say 5 volts or 10 volts or 100 volts. And that's what PS is. PS is our power supply. So what happens if we put a piece of charged metal in the plasma? In this case, negative. So as you would expect from kind of your knowledge of electrostatics, is that you have a negative charge is going to attract positive charges. So ions, these big heavy ions actually come and hit our negative piece of metal. And what happens is actually the metal produces electrons, because remember our power supply is essentially it can give out or it can take in electrons. It can like basically, it can give out current or it can absorb current. And so when these ions come and whack into this metal, what they do is they each get an electron. So they're basically being neutralized, meaning now if this is, say, hydrogen, we now have one proton and one electron. We just have neutral hydrogen gas. But what we can do is we could have measured the number of electrons that are flowing out of our piece of metal, and that gives us a current. So that's something that can tell us about the plasma. So all of what I just described is called Langmuir probes, and this guy Langmuir came up with them. He's also a person who coined the word plasma, which is a fun fact. He thought because it has multiple species, meaning ions and electrons, it reminded him of blood, so he named it after blood. He was the first person to use these kind of probes. You can see in these, there's a bunch of different kinds. There's a big sphere like we were just talking about, but you can also do these tiny little rods. I'll show some pictures of Langmuir probes I've built in the past. But yeah, so you can bias or charge or apply voltage. That's all the same way of saying the same thing positively, and you can collect electrons. You can bias negatively and collect ions. And you can also change the voltage. You can go from a negative potential all the way to positive potential and measure everything in between. And you can learn a lot about the plasma, including the density and the temperature. So we're back to our applying voltage in a plasma. So we've neutralized these, but kind of what it's going to do is it sets up this thing called a sheath. And it's this area around the probe that is being affected. The plasma in this area is being affected by our potential. And one of the key characteristics of a plasma is that it shields those charges eventually. So any free charge, if you apply some test charge, which is what this is, some charge to the plasma, at some distance away, the plasma will rearrange itself to shield that electric field. And in this case, the case of a charged piece of metal, we call it a sheath. So if we increased our potential, that sheath would get bigger. And so then we're going to attract more, in this case, because it's electron, more ions and push away more electrons in this bigger area. Okay, a little more about Langmuir probes. So yeah, we bias the probe negative. We can collect ion current, so we're getting ions interacting with it. And then at high probe voltages, the sheath eventually saturates. So if you and keep increasing the voltage, eventually the plasma will kind of settle on one sheath and it won't get any bigger than that. This is an example of a sheath of a kind of rod. If you sweep a Langmuir probe, these are kind of busy, but hang with me. So in this top red line, I've swept my Langmuir probe from minus 15 volts to 25 volts, and you get this kind of like squiggly line. And basically down here, you're collecting ions and it's kind of saturating. Remember I mentioned saturation. And then up here, you're collecting electrons. And so in between here, if you take the logarithm of this line, you get data like this is data I produced. And you can measure kind of the slope here. You can measure the slope here. You see where they interact, and you can learn all sorts of stuff, like electron temperature and this plasma potential. So these are very simple things. They're effectively just pieces of metal. And if you use them in a specific way, you can learn a lot about the plasma, but they do require interacting with the plasma. These are just some more types of Langmuir probes. These two on the bottom right and left are ones I've built. This is a triple Langmuir probe. You got 3 little prongs. This is kind of this big flat disc. There's a bunch of different ways, and you use them for different purposes. These are used quite extensively in low temperature plasmas. So they're used in space. This is a picture of a satellite, and these two rods look like this. I think they're about 6 inches long or something. And these are Langmuir probes used in space. And then this is a picture I took of a Hall thruster, which you remember from the last lecture. And this arm over here actually has a Langmuir probe on it. And it's about 80 centimeters away. So in that case, we kept it a little farther away. We do use them in tokamaks. We use them at the very, very coldest areas of the tokamak because anywhere hot, like the diverter, they would just melt. So we use them in the scrape-off layer to measure kind of the very periphery of the tokamak plasma. Okay, so another probe, it's called an energy analyzer. There's two different kinds we're going to talk about. One is called retarding potential analyzer. The other name is Faraday cup. And it's essentially to tell us about the energy distribution. So if you look at the picture on the right, the x-axis is velocity, and the y-axis is basically the number of particles in that velocity. So velocity is similar to energy, in this case, kind of like the energy coming in direction from left to right. And if we use this RPA, we can basically build this energy, this velocity distribution. So most of our particles have this velocity. In this case, we've labeled 0, but you can normalize this however you'd like. And then some have velocity going this direction, some have velocity going this direction. And we do this by having the series of grids. So what this is, it's a little cylinder. One end's blocked, and one end has these kind of screens, like a screen on your window. And we apply different voltage to these screens. So the first one might be floating to kind of make sure we're not affecting the plasma around us very much. The second one is very negatively charged, so it rejects electrons. You can see this electron being bounced back. And then the third one might be charged to some positive potential so that you only allow certain energies, so certain speeds of ions to pass through and get to your collector. So now we know at like a one operating point, so one set of these voltages, we know how many particles are coming in to have a very specific energy. So that's a very useful thing. And then we can move these voltages and we can build a plot like this. The other way to do this is called an electrostatic analyzer. These are used really widely in space plasmas. There are a bunch of satellites around Mars and around the Earth that have these, they're usually dome-shaped, that measure the energy of just like ions flying around between the planets. And what this is quite similar, but you basically have this semicircle, and you apply a voltage to the inside, so that the outside and the inside are both pieces of metal that are separated from each other. So you apply negative voltage to the inside and a positive voltage to the outside. And all these arrows are potential ions that are flying into the entrance. And you want to just collect ones that have a certain range of energies. So in this case, my yellow one has no charge, neutral particles, so that doesn't get affected by the electric field. So it just whacks into this metal and bounces around and leaves. We have green, which is low energy, so this is coming in kind of slow, and this gets sucked into the bottom. Then we have blue, which is kind of the target energy that we're looking for, and that, because it has the perfect speed, it gets pulled by this negative, but it still has some inertia, and it gets pushed by this positive, so it like makes the bend perfectly and hits our detector. And then high energy is it's going too fast, so it's going too fast to be affected as much as it needs to be by this negative and positive voltage, and it runs into the wall. The other way to think about this is if you had kind of like a track in Mario Kart that's, it bends up as you're going around the corner. And if you're, kind of like driving straight, or a marble on a curved track, or a coin, any of these things, if you're going too slow, you're going to slip off and go on the inside. If you're going too fast, you're going to go straight and fly off the curved track. But if you're going just right, you're going to bend around the curve. Your marble or your coin or your little Mario Kart guy is going to bend around the curve and make it to the other side of the thing. And that basically tells us that the number of ions coming into our detector that have a specific speed. In this case, that's what we're interested in. And that gives us an energy distribution function, which is this plot here. Because again, we can change these voltages and see at each specific velocity how many particles are there. These are used, again, in cold plasmas. We put them in a tokamak, they would just be completely melted. But the top two are ones I've worked with these little plasma rockets that we do ground testing with. And you can also use them in space. So this one is the sensor on the bottom right is on the Parker Solar Probe, which is a really important satellite rotating the sun. And it's doing exactly what we just talked about. It's measuring the energy of the ions flying out of the sun. They also get used in interplanetary missions, like I mentioned, MAVEN and MMS. TRACER are three big ones. If you want to look those up, they're very cool. All right, so now we're going to talk about interferometry. This is a pretty specific application, but it's very important, especially for tokamaks. So we mentioned last time in the non-fusion plasmas about the ability of plasmas to reflect certain frequencies of light. And basically, if the frequency of light is not fast enough, if the frequency is not high enough, the plasma might it might bounce right off. You remember this? We talked about this with radio waves bouncing off of the ionosphere. So this cloud of plasma around the Earth, we fire a radio wave up at it and it bounces down. And that's how our radio stations work and things like that. In this case, what we're doing is we're firing light through our plasma, and we're basically seeing A, if it bounces off, and then B, it might be slowed down. So it might make it through, but it might be slowed down slightly. And that tells us about the global kind of like holistic characteristic of the plasma. And this gets used in basically every tokamak in existence. Okay, so this is our setup. This is called an interferometer. And we fire coherent light. So these are our light waves. You see they're all lined up. This is a laser probably. And so they're all lined up. And then we fire it through this mirror, which is partially transparent. So some of the light goes through and some of the light gets reflected. So we're just splitting the light in half perfectly. They're not being changed at all. They're not being modified. One side goes to a reference mirror. So this is just some mirror. This is all vacuum. So nothing's being changed. The light is exactly what we emitted it at. Then it comes back and again passes through our kind of half mirror, half window, and it gets to our detector. The other branch of light goes the same distance. So these are the same distance, these legs, but it goes through our plasma. The purple is our plasma. Bounces up our mirror, goes through the plasma again. It can go through once if you want it to, or it can go through twice. And then again, and then in this case, it bounces off the mirror and goes to the detector. So what we get is we get our two coherent waves. So these are still the same. They've just been split by this splitter. But then when they come back, when they go through the plasma and come back, this one has actually been shifted slightly. It got slowed down. It's like, got rolled through some molasses or something. It got slightly slowed down. So then when they get collected by the detector, the red one is now slightly off of the blue one. And then they interfere. So you think about sound waves or any kind of thing you learned in physics, where two waves can interfere constructively and destructively. And basically you can see by just collecting the single frequency of the interfered light, you can actually see a difference in the signals, and that tells you about the density of your plasma. It's very reliable. It's again, it's used in basically every tokamak plasma. It gives you the kind of average overall density of your plasma. So this is something to mention is that the speed of light isn't a constant. The speed of light c is the speed of light in a vacuum, so that is a constant. But if you change the medium that the light is going through, so air or water, or in this case plasma, the speed changes. So that's that slowing down going through the plasma. This is the frequency that we're kind of interested in. This is a light wave in a plasma. And what we see is that the velocity of the light is actually slightly different depending on the plasma frequency, PE. So this is the electron plasma frequency. And so our velocity of light is dependent on that, and that is dependent on density. So what we can see is that plasma frequency is dependent on density. The rest of these are constants. So the velocity of the light, and therefore we measure the velocity by measuring the interference, tells us something about the density. So this is used in every tokamak. All right, magnetic diagnostics. We're a ways in, and this is maybe the most important one for tokamaks. Because as I mentioned, tokamak plasmas are so hot, it's really hard to measure them. Doing spectroscopy is really important and is very effective, but there's some things that you can't measure with magnetic diagnostics. And also magnetic diagnostics are usually the easiest, and maybe not easiest, but they are the cheapest to set up, and we'll talk about why. Okay, so this is all using the concept of Faraday's law and Lenz's law. So Faraday's law is basically when you have a changing electric field, when you have a changing magnetic field in time, it produces a curving electric field. It's one of Maxwell's equations. It's super important, and that's what we're going to use. And if you kind of mush around Faraday's law, you get something called Lenz's law, which is the EMF, which is just voltage, same thing, the electric potential, these all mean the same thing. And that is produced by a changing magnetic flux. So our B here is our magnetic field strength. Flux is the magnetic field strength through some area. So it's literally flux per area. It's magnetic field per area, which we call magnetic flux. So if we have a changing flux through some areas, if I draw a circle and there's some magnetic field going through, and then I turn down the magnetic field really quickly, what it's going to do is it's going to create a potential going around the magnetic field in some direction. So this is Faraday's law, and this is what we use to measure magnetic fields. This is mostly what I just talked about. We have a coil of wire, we have some circuit, and if we have our B here, we change magnetic field. So say it goes down really quickly, it goes up really quickly or whatever, it creates a current in this wire. Again, remember I mentioned that all we're ever really measuring is voltage and current. So that produces a voltage. We will measure that voltage with this integrator circuit, and that can tell us something about the magnetic field. So this, if you note that this only measures changing magnetic fields. So we can keep track. So if we know the magnetic field starts at 0, say, and we keep track of all the changes, we can add that up to know the kind of absolute. But another way which is called an integrator. So basically what we're doing is, okay, so magnetic field started at 0, and I know in the last second it went up 1 Tesla, say. Now I know I'm at 1. If it goes up another 1, now I know I'm at 2. So that's called an integrator, basically keeping track. But those often have drift. So there's some error, and that error builds up over time. So we can use things called Hall probes, Hall effect probes, which work quite differently, but they measure steady state magnetic fields. So this is a drawing of a tokamak, and these are all the different kinds of magnetic sensors we use. And I'm going to ask you to guess which one of these measures the specific plasma quantity or whatever that we're interested in. And I'm going to ask you to guess. So all of these use the same concepts we just talked about. They're all loops of wires, so they all have some loop. So this diamagnetic loop goes around poloidally. This magnetic field probe is just a little loop kind of off to the side. You can put them anywhere. A flux loop goes all the way around toroidally. A saddle loop is this kind of square or a circle that's kind of on the side of the tokamak. And it's called a Rogowski coil. It's actually each of these little loops is the loop that we're interested in. So it's the magnetic field going around this way. Okay, so if you had to guess which one of these gives you some indication or measures the plasma current. So it's the toroidal current going this way. And again, pause and think about each of these because it is important. Obviously, don't get them. That's totally fine. But you can figure them out just by kind of doing your right hand rule. Okay, so plasma current is measured by the Rogowski coil. That's this guy because the plasma current is going through the loop and is producing a magnetic field going this way. So if our plasma current changes, it changes magnetic field going through this loop, and that causes our voltage. Poloidal flux. So that's the magnetic flux going in the poloidal direction. So in this case, that would be going like this. So what magnetic field would that create, and what would we use to measure it? The flux loop. So that's this big one. So that's because the poloidal flux is going up and down on either side of here, and that changes the flux to this big loop. Toroidal flux. So that's the flux going kind of around the donut. So if that changes, we turn that down or turn it up quickly. Where would that be able? Where would we measure that? This one, the diamagnetic loop, because the poloidal field is going through. This may be the most straightforward one to explain. The toroidal field is going through here, and when we change, say we reduce the toroidal field really quickly, it excuse me, it changes the voltage in this loop going around poloidally, and that's a diamagnetic loop. So what about radial flux? So there's some magnetic field coming radially out of our plasma. How would we measure that? The saddle loop, this one. So that would be the magnetic field's going through this square. If it changes, we can measure that. And then finally, local flux. This is kind of a broad one, but you can put these magnetic field probes anywhere. And it turns out they are kind of everywhere around the tokamak. And you can measure the field here, which is produced by the plasma usually, and how is that changing over the course of a plasma. As I mentioned, they're everywhere. All of these little dots. So this is ITER. All of the pluses are this external sensor, but each one of these symbols all the way around the device is a magnetic probe. And that's just one cross section. Those are propagated all the way around toroidally. So D3D, which is operating tokamak in San Diego, has 168. It probably goes up and down, but that's a lot of sensors because these are used for operating the tokamak itself, for learning, doing all sorts of scientific discoveries. So these are super important. They're also non-invasive. They don't affect the plasma at all, which is really great. They can detect instability. So little things are happening in the plasma very quickly that we don't want to happen or aren't planning on happening. We can measure those, and sometimes we can use those to actually actively control the plasma. So this would be, sensing what is going on wrong with the plasma and then reacting to kind of fix it very quickly. All right, so the last kind of diagnostic we're going to talk about is neutron diagnostics. I mentioned this before, but if you remember when we do deuterium-tritium fusion, which is the kind of fusion that we are trying to do right now, we being the field of fusion, you have a hydrogen with one neutron, so that's deuterium, and then you have hydrogen with two neutrons, which is tritium. You collide them together. If they have enough energy, they will fuse together. And what they will do is they will kick off one neutron with some really high kinetic energy, and then one helium. If you add up, you get, we have two protons, that's two protons. We have three neutrons, we have three neutrons. Okay, cool. The product of this, again, is this charged helium atom. So now we've made a helium atom or helium nucleus. And then we get this free neutron. And 14 MeV, this is mega electron volts. It's a unit of energy. It is a lot. These are very high energy neutrons. And what they do is they just leave the machine because everything, all of our plasma is confined in magnetic confinement by magnetic fields, by magnetic and electric fields, which are the same, electromagnetic fields. Neutrons aren't affected by those, right? They are neutral. They don't have a charge. So they just, whatever direction they're produced in, which is any direction, it's completely random, they just fly off. And these neutrons are so fast that they will go through most materials. They'll go through metal, they'll go through concrete. You need basically either a lot of concrete or lead or something super dense to slow them down. Um, and like, they can penetrate through feet of material. If you ever visit a tokamak, you'll walk around walls that are feet thick of cement to try to block these things. But what that can tell you is it can actually tell you exactly where the fusion is happening and how much fusion is happening. There's no other, like when you produce that helium ion, hopefully it stays confined in the plasma and adds energy back to your plasma. So it's not leaving at all. And there's other signals, but this is kind of the clearest signal. If we see really high energy neutrons, specifically if we see 14 MeV neutrons flying out of a certain area of the plasma, we know that fusion is happening there and we know how much. So this is a really important metric that is used today in all the big tokamaks around the world, but will be more important as we get really highly effective, like tokamaks that produce a lot of fusion energy. So you measure these with a few different ways. One of the most interesting ones is a fission chamber. So we're trying to do fusion. Fission is the standard or traditional way of making nuclear energy. And that is you take a big nucleus, so in this case, uranium-235, and you hit it with a neutron and it splits in half and makes fission fragments and all sorts of other things you can detect. So one way we can do that is usually you do that to collect the energy that is produced by fission. But in this case, we have a cylinder. I think they're about a foot long, and you have it somewhere near your tokamak, and your neutron flies in. So in this case, your neutron flies in, and the cylinder is lined on the inside with this layer of uranium-235. So uranium-235 will not split in half on its own. It needs a neutron to hit it. And it can split in half with low energy neutrons, but it can also fission with high energy neutrons. So in this case, we have this high energy neutron coming in, it slams into our uranium and splits it in half. And this FP is fusion products. We can measure those fusion products using all sorts of different methods. In this case, current, remember we talked about voltage and current. Those are the two things we can usually measure. In this case, we're measuring current. So this is a signal of this neutron because remember, neutrons don't interact with things. They're really hard to slow down. So measuring them directly is really hard. So what we usually do is we set up a scenario where the neutron flies in, it affects something else that is easier to measure, and then we know that a neutron hit it because otherwise these fission products wouldn't be produced. Another way is a scintillator and photomultiplier tube, which we talked about earlier. So instead of light coming in, you can have a neutron come in. It whacks off it hits some material, a bunch of electrons are kicked off, and those electrons are multiplied down this photomultiplier tube, and we measure the electrons at the end. So same thing, neutrons are really hard because they don't interact with much matter. They're really hard to detect, but we give them a scenario where they produce a signal. They interact with some stuff, and they produce a signal that we can then measure. So this is important and is used in all the big fusion devices experiments going on today, but will be increasingly more important as we get higher fusion energy. So this is an example of Spark, which is a tokamak being built in Devens, Mass. That should produce a lot of fusion, and so they are doing lots of neutron diagnostics. And this is kind of a picture of, I think I have a picture next. Yeah, this is the tokamak hall. So this sticker on the wall is the tokamak, but it will be in the center. And this massive slit in the diagnostics wall, again, I think this wall is like 6 feet thick of concrete, something like that. It's very significant. But this big kind of vertical opening is for neutrons. And what they're doing is they have all of these neutron detectors lined up like this, and it's kind of like a lens. They're all looking at very specific parts of the tokamak. So if I have fusion here and a neutron is produced, it will go down here, it will go through this barrier, which is probably lead, and it will find this photomultiplier tube. And it then will give me some signal that some amount of fusion is happening right here. So this is very important for them because they need to show the world that they are doing lots of fusion and they're producing more energy out than in, and that's a big goal of this machine. All right, so as a brief review, this is it. But to go back over what we talked about, spectroscopy is measuring light. You can do it actively by adding energy to the plasma and then seeing the light that is produced. or passively just by looking at the light that the plasma produces and making decisions or conclusions from there. Probes, you're actually putting metal into the plasma and changing its potential and collecting current and voltage. It's hard in some ways because your metal probe might melt. You're also affecting the plasma. You're applying this piece of metal to the plasma and it's changing the plasma, so you have to account for that. Magnetic sensors are super important. They are passive diagnostics and they're used widely and constantly in tokamak, so they're really important. Interferometry is passing light through a plasma, seeing the phase shift, which is that change in speed as it slows down going through the plasma. This is important for measuring density. And then, of course, neutron diagnostics we just talked about, which is a really important way to measure the fusion we're doing in a fusion tokamak. So that is it. Thank you.